The final topic in our course this semester will be a hypothesis test, a significance test called analysis of variance, which we often abbreviate ANOVA for short. I wanted you to have this experience. This is one of the things that we're probably going to run out of time for this new format, but the reason this is important is that this is a test for association. So it's a test for association between a categorical variable and a quantitative variable. So we're going to do this in a couple of videos. I'm going to give you the basic idea in this one. So it's probably good just to skim these notes, and then we'll do one example. The way the test works, it seriously needs technology to do the calculations. So I will show you what the output from the technology looks like and try to make sure you understand what you're looking at. But we definitely are going to execute this test by carefully stating our hypotheses and assumptions, letting the technology do the math part, and then writing sensible conclusions. So when we have a categorical variable, then the answers to the categorical variable will break our population into categories. So if one of our categorical variables was, what is your gender, then that immediately breaks our population into two groups, male and female. So when we refer to the groups, what we're in these problems, what we're referring to is the people who answered a particular way to the categorical question. Because we're looking for association between that and a quantitative question, that means that for each of those groups, they were all asked the same quantitative question. And so for each of those groups, that quantitative question will have a mean for that group. So officially, what we do with analysis of variance is compare the means of the population, the means in the population of the answers to the quantitative questions across the different groups for the categorical question. So that may sound a little confusing, but it makes a lot more sense in an example. So when we have groups, the letter G here is referring to the number of groups, and that just means the number of possible answers to the categorical question. This slide is trying to tell you what the general hypotheses and testing is in the setup in general. I'm going to skip forward to talk about just what the test is doing, and then in the next video we'll see an example where we actually set these hypotheses up. The most important thing is that since we said this is a test for association, the most important thing is to realize that H0 is really the statement that there's no association between the variables. The reason the way that it says that is it says that within each group, the mean answer to the quantitative question is the same. If the quantitative question has the same mean in every group, then there's nothing special about the grouping in terms of influencing the answer to the quantitative question. So if H0 is the statement that there's no association between the categorical variable and the quantitative variable, then HA is that there is some association there. So that's how we're going to think about our H0 and our HA. It's nice compared to some of the other significant tests that we've done, because in that sense, H0 and HA are the same in every ANOVA test. H0 is always the statement that there's no association between the quantitative and categorical variable that are involved, and HA is always the statement that there is some association. So we don't have to read a problem real carefully in order to decide what our H0 and HA statements are. So for analysis of variance to work correctly, there are some assumptions that we have, and as usual for a class at this level, we're going to sort of set problems up so that these assumptions are satisfied and not get into too much detail about what do you do if they're not. As always, randomization is an important assumption, meaning that when we grab our sample from our population, that we're doing that randomly. There is an assumption for analysis of variance that within each group, the response variable, that's the quantitative variable, is normally distributed more or less. And ideally, you'd like to have roughly the same standard deviation for each group. Those are sort of ideal goals for analysis of variance, but we can get away with not exactly satisfying those, and we'll still get a decent result. And as usual, the larger the sample size, the less those assumptions matter. So here's a quick example using numbers from our textbook that just shows the idea of how the test statistic for analysis of variance works. This is an example where there was an experiment done to see how long people would stay on the phone on hold, depending on what they hear while they're on hold. So the people doing the study randomly sampled 15 people, and 5 people heard advertisements while they were waiting. 5 people heard classical music while they were waiting, and 5 people heard music, like elevator music, while they were waiting. And the amount of time that they held before hanging up was recorded in each case. So this was an awful experiment to do to people, see how long they'll stay on hold. But I guess that's why they didn't do it with more people. So there's 2 different situations here. And the reason is because this is just a fictional example where we're seeing in which case we would feel like there really is an association. So an association in this case would mean that the holding time is different depending on what you hear. That's what we would mean by saying there's an association between what they're listening to and how long they stay on hold. It would mean that their holding time is definitely different depending on what they're hearing. So that would be the statement about having an association between the 2 variables. So these are 2 different scenarios with 2 different data sets, just to point out when we might be comfortable deciding that there really is something going on. And the point here is that in the first example, the people listening to an advertisement are very spread out. In the second example, the people listening to the advertisement are not very spread out. Now, you can't tell just from those dots, but those 2 groups, the 2 things I just circled in green, actually have the same mean. But in the second case, in case B, we feel like the mean for this group is actually pretty accurate as a representation of how long people will stay on hold if they listen to an ad. And that's because the variance of this group of dots seems like it's a lot smaller than this one. The spread of these dots is much smaller than the spread of these dots. So if you told me I have these 5 dots that average about 5, I'm not completely convinced that the average could not be 8 or 3 or whatever. There's could be some random variation here. But for this one, because they're so tightly clustered, if you tell me that the average of these is 5, I'd say, yeah, that's probably about how long people stay on hold if they listen to advertisements. And so notice that that's actually true. The way this is set up as an example, we have the same thing going on for each group. So here are the 5 people that listen to classical music in the first example, and here they are in the second example. And again, in the second example, since they're so tightly clustered, we would believe if you told me that cluster's average was about 10.5, I would say, yeah, I think that's probably about how long people listen to it because of how closely grouped that those data are. And finally, the same thing's happening here. People listening to music spread out from 0 to 6 minutes in this example, all clustered between 2 and 4 minutes in this example. So taking all that into account, it seems like you could make a conclusion from the second case and feel a lot more confident about it than a conclusion you'd make from the first case. Again, the groups of dots have the same means in the top picture and in the bottom picture, but if the data were clustered as they are in the bottom one, I would feel like the 3 means for those groups are more indicative of what's really going on instead of the one above that's more spread out. So the two terms, when we see this picture, there's two terms that you'll see thrown around. We talk about the variability within each group, and we talk about the variability between groups. So here, this has a higher variability within the groups. The variability between the groups is actually the same in each case, because when we talk about variability between the groups, we're talking about how different the actual means of these groups are. And like I said, the means of the three groups in example A are the same as the means in the three groups in example B. So the between groups variability is the same in these pictures, but the top pin has a much higher within groups variability. If I draw those two different cases as box plots, we can see it a lot more easily. We also can verify here what I said about the means being the same. So these are the two cases again. The means are identical for those three groups. Notice on the left, the box plots are really, really spread out. And we know that from both that's indicated by both the standard deviation numbers here being much larger than the standard deviation numbers here. And also we can see it from the IQR numbers like we've seen before. So the spread, which is measured by these two guys, is much larger in the left picture than it is in the right picture, even though the means themselves are exactly the same. So again, the idea is that we believe that a conclusion based on the picture on the right would be more valid about saying whether these means were very different or not. So let me just show you the formula, test statistic. It literally is involves the two things that I just said, but it's measured as a quotient. So it's the between groups variability divided by the within groups variability. I'll show you on the computer output in the next video where those numbers come from. We don't actually have to calculate those, but by understanding that F is made up of the quotient of these two things, it does help reinforce our intuition about how that F test statistic changes when you have examples with more or less variability. So what we just said from the example is that if you have a higher, well, let me say it the other way around. If you have low within groups variability, so that would mean you're making this denominator small. The way fractions work, making the denominator smaller makes the whole fraction bigger. So lower within groups variability is going to make that F score higher. And what we just said was having lower within group variability means that those groups were more clustered, and so that's actually better. So we think that would give us better, more evidence of association. So this is really the takeaway. The example we just showed had both of the case A and case B had the same between groups variability. So this numerator in those two cases were the same, but one of them that was more clustered had a smaller number in the denominator. So smaller number in the denominator means bigger fraction. So ultimately, this is going to be the case, and this is the way we want to think about things. The higher this F number is, the more evidence we have of having an association between our variables. So that's the main idea that we'll take forward, and we'll see how that F score comes out of a software package and how we can then make a conclusion about our hypotheses.